this video, we'll look at a few interpretation questions you might get on functions. We'll start with calculations to determine whether a function is increasing or decreasing. Then we'll explore a function's concavity and its extrema, absolute and relative, and finish with some theorem questions, including the intermediate value theorem, Rolle's theorem, the mean value theorem, and finally the squeeze theorem. All right, let's jump in. The first question is whether a function is increasing or decreasing at a specific point on its graph. If we have the sketch, it's easy. Imagine walking along the curve from left to right. Are you going uphill or downhill? Anywhere to the left of the turning point, you go downhill, so the function is decreasing there. To the right of the turning point, you go uphill, so the function is increasing. At the turning point itself, you're flat, so the function is neither increasing nor decreasing. Mathematically, we want to decide this even without the sketch. It all comes down to the slope at that point. If the slope is negative, the function is decreasing there. If the slope is positive, it's increasing. And if the slope is 0, you're at a turning point, so it's neither. To find the slope at a specific point, we use differentiation. Take the first derivative of the function, then substitute the given x value to get the slope. A positive result means increasing, a negative result means decreasing, and 0 means neither at that instant. Let's take an example. In this example, they ask us to determine whether a function is increasing, decreasing, or neither at x equal to 5. Right away, we see we don't have the sketch. We could draw the sketch and check what happens at x equal to 5, but that's way too much work. Instead, we can just find the slope at x equal to 5. How do we get the slope at a point? We differentiate the function once and then substitute 5 into the differentiated expression. Remember, when we differentiate any function once, it gives us the slope of the function. Using our usual circle trick, we obtain an expression for the slope. Now all that's left is to substitute 5 and see the result. If we get a positive value, the function is increasing at x equal to 5. If we get a negative value, the function is decreasing there. If we get 0, the function is neither increasing nor decreasing at that point. When we substitute 5, we get positive 25. That means that if we had sketched the function, we would see that at x equal to 5, the function is increasing. In other words, you'd be walking uphill from left to right. The second kind of interpretation question they can ask about a function is the concavity at a specific point on the curve. In plain English, concavity just means whether, at that point, you are on a smile part of the graph, concave up, or on a frown part, concave down. If you look at a typical sketch, the left half of the function might form a frown and the right half a smile. Exactly in the middle is the inflection point, the precise spot where the concavity changes from frown to smile, or from smile to frown. So any point to the left of the inflection point lies on a frown section, concave down, and any point to the right lies on a smile section, concave up. Just like with increasing and decreasing, you will not always get the sketch, so we need an algebraic way to decide this. We do it by using the second derivative, meaning we differentiate the function twice, and then substitute the given point into that expression to check its sign. If the value is negative, the point is on a frown section, so concave down. If the value is positive, the point is on a smile section, so concave up. If the value is 0, the point sits at the inflection point itself, the exact place where the function switches between smile and frown. All right, let's look at an example. In this example, we can see that we again do not have the sketch to check whether x equal to 5 lies on a smile, a frown, or the inflection point. And just like with increasing and decreasing, it would be far too much effort to draw the sketch, so we use algebra instead. We determine the second derivative and substitute 5 into that expression. Once we have the second derivative, we put 5 in and look at the sign of the result. If it is positive, the point lies on a smile section of the graph, concave up. If it is negative, the point lies on a frown section, concave down. If it is 0, the point is exactly at the inflection point, so it is neither concave up nor concave down. When we substitute 5, we get positive 20, which means that at x equal to 5, the point is on a smile part of the function, concave up. The third type of interpretation question they can ask is about extrema. What does that mean? Extrema are simply the high points and low points on a function. These points can occur either at critical points, the turning points, or at the endpoints, which are where the function begins or ends on the interval you are looking at. There are two kinds of extrema, and they're easy to tell apart: relative, also called local, and absolute. A relative extremum is any visible high or low point on the graph when you zoom in near that point. An absolute extremum is the single highest or the single lowest point on the entire portion of the function you are considering. The graph never goes higher than that highest point or lower than that lowest point. If we look at a sample function, it's easy to spot all the highs and lows. Every high or low you can see inside the interval, away from the edges, is a relative or local point. It's very important to remember that endpoints, the start or end of the interval, can never be relative or local extrema because they're just where the graph gets cut off. So in our example, we might see relative maxima and minima at points B and C because those are turning points. We do not have relative maxima or minima at points A and D because those are endpoints. That means B is a relative maximum, a high point, and C is a relative minimum. To find the absolute extrema, we look for the single highest and the single lowest points on the whole interval. In this example, the lowest point is C, so C is the absolute minimum. The function does not go any lower than that. Here's a detail that can feel a bit confusing at first. C is both a relative minimum and an absolute minimum. When we look for the highest point, we see that the top of the graph is D, which is one of the endpoints. D is the absolute maximum. But be careful, D is not a relative extremum because relative extrema cannot occur at endpoints. So D is only an absolute maximum. One more thing to keep in mind is the notation used for endpoints. An endpoint can only be an absolute minimum or maximum if that endpoint is included in the interval. In interval notation, that means the endpoint is written with a square bracket. If the endpoint is excluded, written with a round parenthesis, then it cannot be an absolute extremum. Let's look at an exam-style question about extrema. In this problem, we are asked to find the extrema for a given function. Just like with increasing, decreasing, and concavity, we can see they haven't given us a sketch, so we need to work it out algebraically. Here's the plan. First, find the critical points. These are the turning points, and, as you may remember from the previous video, we get them by setting the first derivative equal to 0. Next, use a number line. Place the critical points on the line as well as the endpoints of the interval. Finally, interpret the number line to decide where the function has relative minima, relative maxima, and which point, if any, is the absolute minimum or absolute maximum. Let's do the example together, and these steps will make perfect sense. For our first step, we'll find the critical points by taking the first derivative and setting it equal to 0. Differentiate once, set that expression to 0, and solve for the x values of the critical points. Then substitute those x values back into the original function to get the y coordinates of the critical points. Now we have the turning points on the graph, and we know extrema occur at turning points. Pause the video to make sure you're getting the same answers as I am. For our second step, we're going to place the critical points on a number line along with the endpoints. Make sure the number line is in the correct order, small to large, and remember, we only use the x values of the critical points and the endpoints. The last step is to interpret the number line. We do this by using the first derivative as a sign test. Pick a simple test number inside each interval and substitute it into the first derivative. For the first interval, between -3 and -1, choose -2. For the next interval, between -1 and 1, choose 0. For the last interval, between 1 and 3, choose 2. The second part of the interpretation is to plug the actual x values, meaning the critical points and the endpoints, into the original function to get their y values. Pause the video and check that you get the same results. Now, what do these values tell us about the extrema? For the first derivative, we only care about the sign we got when we plugged in the test values between the points on the number line. Remember, the first derivative tells us the slope, and we said at the start of the video that a positive slope means the function moves uphill, while a negative slope means it moves downhill. From this, we can see how the function must move, because at -1 and at +1, we established there are turning points. In the second part of our number line work, we substituted the actual points from the number line into the original function to get their y values. Those y values tell us the heights or depths of the function. So we see the function starts at -3 with a height of -18. Then we have a turning point at -1 with a height of 2. Then another turning point at 1 with a height of -2. And finally, the function ends at 3 with a height of 18. We can now use this information to make a rough sketch, which helps us identify the extrema. So this is a quick sketch of our function. Look closely at the endpoints they gave us. The left endpoint at -3 is excluded, so we mark it with an open circle. That means we cannot use that value as an absolute extremum. The function ends with an included endpoint, so that one could potentially be an absolute extremum. Now, looking at the rest of the sketch, we can identify the extrema. Working from left to right and starting at -3, that point is not an extremum. Next, at -1, we have a relative maximum, because it is not the highest point on the entire sketch. Then at 1, we have a relative minimum, because it is not the lowest point overall. Finally, we end at 3, which, on this sketch, is the absolute maximum, since it is the highest height the function reaches. And that's the question done. The fourth kind of interpretation question is about our theorems, and we're going to look at 4 of them. It sounds scarier than it is. Let's start with the first one, called the intermediate value theorem. A theorem is simply something that is always true, and because it is always true, we can use it to solve tricky problems. Think back to school geometry. You had a bunch of theorems you could use to solve problems, like the fact that the interior angles of a triangle always add up to 180 degrees. You could use that statement to work out unknown angles in a triangle. In the same way, we have theorems for functions. The first one, the intermediate value theorem, says this. If you have one point on a function that lies below the x-axis and another point that lies above the x-axis, then, provided the function is continuous between those 2 points, there is at least one place where the function crosses the x-axis. And the point, or points, where the function crosses the x-axis will lie between those 2 points that sit above and below the x-axis. Let's look at an example together. The full video is only available to our awesome ebook course students. In our ebook course, all your videos live in one place, together with the ebook and downloadable cheat sheets. No more 2 a.m. doom scrolling on YouTube before a test. Everything's in one spot to help you succeed at Calculus 1 the first time. Let's be honest, I'm not here to convince you of the beauty of calculus. I'm not a professor who can talk for 3 hours about how elegant differentiation is. This is damage control to get you through Calc 1 so you can move on with your degree and with your life. This is your please don't ever make me redo this class again plan. And it's all at a student-friendly price that costs less than a mid-tier restaurant meal. Not even steakhouse level, more like a fancy burger with just one side. See you inside the ebook course.